This presentation is on electrical energy basics. Do you remember the terms you heard in science class? Force, work, power, energy. Do you remember what they mean? Do you remember how they relate to each other? Well, this is what we're going to talk about in this presentation. So let's start with force. Force, very simply, is a push or a pull. It also relates to potential energy. Now let's say we have a car that doesn't go, so we're going to have to push it. And we push with a force. Now work is force times distance. So in this case, we're pushing with a force of 10 pounds. The car is not moving, so therefore work is not being done. The other thing is you might think of work as both force and something moving or something in motion. Now let's say we push a little harder. We push with a force of 20 pounds and we get the car to move 10 feet. We have performed work. The work that we have performed is 20 pounds times 10 feet, or a total of 200 foot-pounds of work. Now the term power has to do with the rate at which work is done. So if we push this car with a force over a certain distance and we measure the time, then we can figure out the power that was used in accomplishing this work. So in this case, we pushed with 20 pounds of force at a distance of 10 feet, and it took us 10 seconds. So to figure out the power, we just simply multiply the 20 pounds times the 10 feet, divide that by 10 seconds, and we come up with 20 foot-pounds per second. Now that is a measure of power, and that's the particular amount of power that we used in this case. So here's our formulas. Force, a push or a pull, force and something moving or motion, or in this case force times distance, equals work. Then power is the rate at which work is done. If we multiply that rate at which work is done times the time, then we come up with the amount of energy that was used. Energy, which we calculated was 20 foot-pounds per second, times 10 seconds equals 200 foot-pounds. That's how much energy was consumed in this example. Now the definition of energy is the ability to cause change, the capacity to perform work. And if you noticed, work was really directly related to energy. Work performed is the same as energy used. See, the two T's cancel out in our mathematical equation. Now let's look at electrical energy. In this case, force is related to voltage, which is also called a potential difference in a circuit. So instead of a man pushing a car, we have an energy plant pushing electrons through a conductor. Now we also use the term current, and the term current has to do with the flow of electrons and the charge they carry over time or per unit of time. For example, we use the unit amp or amperes to mean 1 coulomb of charge passing by a single point in 1 second, or 1 coulomb per second. And that's our current. Now power in electricity is basically voltage, which is the force component, times current, or the flow of electrons or the charge carried by the electrons over time. That is power. So this is the rate at which work is being done. It's also the rate at which energy is being used. Now then, simply energy is power times time. So let's see what this looks like at your school. In this example, we have early in the day the lights coming on. Let's say the custodian gets there early in the morning, turns all the lights on. So now a certain rate of energy being consumed is occurring at a given point. We call that a demand for power at that given point. All those light bulbs demand power in order to light up. And so in this case, the demand for power is a little less than 200 kilowatts. A little bit later in the morning, it starts getting warmer. Air conditioning systems start coming on. So the rate at which energy is being consumed goes up to a little bit over 400 kilowatts. Now we're getting close to lunch, and the stoves and the ovens are coming on, and people are walking in and out of the coolers, and they're having to cycle more because they want to keep their cold temperature. Our power demand is getting very close to 600 kilowatts. Power demand at any given point of the day depends on the demand for electricity at that time. Now let's take a look at power demand over a 24-hour period. We see that the demand for power varies throughout the day. Now early in the morning and in the middle of the night, it's low, in this case about 100 kilowatts. Then as the time goes on and we get closer to school starting, we start using a little bit more, just like in the example we just looked at. Lights come on, then the air conditioning unit comes on, then other appliances come on during the day, computers come on. At some point during the day we reach a peak power, and then energy demand starts to level off and go down. When you add up each of these bars of power, then we can get the total amount of energy used during one day. The curve we use to show the demand for power and how it varies over the day is called a load profile curve. Here's an example of a load profile that was obtained from an electric utility company. It shows a 7-day period, and it shows, you can see on the left, the first day must be a weekend like Sunday, then the 5 work days or school days during the middle of the week, and then it ends on a Saturday. You can see how the power demand peaks during the middle of the day and then goes back down at night. This is a load profile for a 24-hour period, and these can be very helpful. It lets you see when power is being used and how much power is being used over a 24-hour period. For example, in position number 1, we have 200 kilowatts being used in the middle of the night. That seems like a lot of power being demanded. Perhaps there's some things that are on that could be turned off. So that's one point. Point number 2. We noticed at 5 o'clock in the morning, the demand for power spikes way up at 5 o'clock in the morning. Why so early in the day? Well, we may find that air conditioning systems are set to come on very early, much earlier than they need to come on. And maybe they don't all have to come on at the same time. Now, at point number 3, we see that not a lot of difference between our actual and our demand and the ideal, because we need everything going. But there may be a few things we can turn off. For example, there may be some classrooms with computers where nobody's in them. Those could be turned off. There could be some hot water heaters and janitorial closets, and the janitors aren't using them at that time of the day. They won't be using them until later in the day. So there's some things that might be turned off. Point 4, this is after school. And usually what goes on after school is the cleaning process, and you have your custodial workers going through the classrooms. And it could be all the lights in the classrooms are on, even though the janitor, it may be in a different classroom and there's 10 other classrooms waiting and nobody's in there. So it could be some kind of operational change that you could make to have all the lights off and only turn the lights on in the classroom where you're working. Same thing with air conditioning. They may be going full blast with nobody in there. So these are ways that you can look at the power demand and how it occurs over time during a day or a longer period. So this concludes our presentation on electrical energy basics.